This video goes along with the Unit 4 test, which Unit 4 is all about applications of probability. Problem number 1. Will surveyed students at his school about whether they have ever gone snowboarding and whether they own a skateboard. He found that 35 of the 99 students who own a skateboard have snowboarded. Alright, let's start with that. 35 of the 99 students who own a skateboard have snowboarded. Alright, so 99 students own a skateboard. So let's see, okay. So this top chart says 48 students own a skateboard. This next one says 134 students own a skateboard. The next one says 99 students own a skateboard, and the next one says 48 students own a skateboard. Okay, so right there, that's enough information on this particular question to narrow it down, because ultimately they're going to ask us which two-way table correctly displays this data. So there are more things that we can check, but I think we already have our answer. It should be this one. Okay, this should be the one. Now let's check some other information. So now it said 35 of those 99 students snowboarded. Okay, so of the 99 students, 35 snowboarded. Okay, so that matches. Also, let me change colors here for a second, switch to green. There were 13 students who have snowboarded but do not own a skateboard. Okay, 13 students who have snowboarded but do not own a skateboard. Okay, so these are the 13 students who have snowboarded, as you can see because of this column, but do not own a skateboard because of that column. So that matches as well. And 147 students who have never gone snowboarding and do not own a skateboard. Let me switch colors. So 147 students who have never gone snowboarding and do not own a skateboard. Alright, here's that 147. Never snowboarded, do not own a skateboard. So every piece of information matches this chart. Alright, that's why this chart is the answer. Alright, which statement is true about whether Z and B are independent? Well, here's the thing about proving that two things are independent. If Z and B are independent, then that means the probability of Z given B should be the same as the probability of Z by itself. In other words, if these two things are independent, it shouldn't really matter if we're given this additional information. If I took it away or didn't take it away, that's the only difference between these two statements. So what we need to do is calculate both of these things and see if they're equal. If they're equal, then that means they're independent. If they're not equal, that means they're not independent. Alright, so let's start with this one. Okay, the probability of Z. Okay, so the probability of Z, this is the total number of Z's. And here's the total number of everything. So the probability of Z, that's target over total, so that's 297 is our target out of a total of 660. So I'm just going to reduce that in my calculator. Alright, I'm getting 9/20. Okay, now let's check the probability of Z given B. Now, when they talk about something that's being given B, that means B is the whole universe. All right, that's what the second little part means. So if we're given B, that means B here is the universe. This is all that exists. So what I like to do is I like to take the other things that are not B and take them away. All right, because it's all about B. So that means it's not A and it's not C. And that means these totals no longer matter. All right, so this is all there is. Okay, so now, given universe B, now we're going to calculate the probability of Z again. All right, so this is still going to be target over total. So we're still going to be doing the Z's divided by the total. So the Z's in this smaller universe, the given B universe, the number of Z's is 126 out of a total of 280. Okay, so let's see what this reduces down to. Nine twentieths. That is the exact same thing we got before. All right, so 9/20, 9/20. So if both of these are equal, that means that Z and B are independent. So let's look and see. Right away we can throw out the ones that say are not independent, because we just found that they are independent. Okay, so Z and B are independent because Z given B is equal to the probability of Z. That's what we just found, so choice number 1. Z given B is equal to the probability of B. Now, it's like it should match the first one. All right, let's do the reveal and make sure that we are right. And of course we are. Alejandro surveyed his classmates to determine who has ever gone surfing and who has ever gone snowboarding. Let A be the event that a person has gone surfing. Let B be the event that the person has gone snowboarding. Which statement is true about whether A and B are independent? All right, so again, here's the part that you basically have to memorize. If A and B are independent, then that means the probability of A given B has to equal the probability of A by itself. So we just need to calculate both of these and see if they're equal. Okay, so I usually like to start with this one. All right, the probability of A. So, all right, the probability of A, well, that's the surfing. So let's see, how many people have been surfing? So when we do probability, we're talking target over total. So we're looking for people that have surfed. All right, so that's 225 people have surfed. All right, out of a total of 300 people altogether. All right, that's 3/4. All right, now let's calculate the probability of A given B. Given B means that B is the new universe. All right, so we're only looking at the universe of snowboarding. So this is the universe, people that have snowboarded, because that is B. So that means these people that have not snowboarded, for the rest of this problem, they do not exist. Okay, this is the universe because that is what we are given. Now, in this smaller universe, we need to find the probability of A. So probability is still target over total. Let's put it right here. And A is still people that have surfed. All right, so the people that have surfed, that's 36 out of a total of 48 people in this smaller universe. So 36 out of 48. Oh, look, 3/4 again. Okay, because we got the same thing for the probability of A given B and the probability of A just by itself, that means that these are independent. All right, so first of all, looking at the two of these answers say not independent. So we can forget about those. All right, it's going to be one of these first two. So let's just see the one that says what we did. They both have the probability of A given B is equal to the probability of A. All right, they both mention that. But they say what that is. Which one of these numbers is the same as 3/4? Well, that is 0.75 is the same as 3/4. All right, that's why it's the second one. All right, for this problem we are to find the probability of C given Y. When they give us something like this, given Y, that means Y is the universe. Okay? That's what I think whenever I see that. So we're given Y. So if Y is the universe, okay, that means this is now the universe. That is what we're given. That means we can throw out X and Z. And these totals are now incorrect because the universe is much smaller. Now, given universe Y, let us go ahead and calculate the probability of C. Probability is target over total. So if I'm talking about C is my target, there's 15 of those out of a total of 30. We know that 15 out of 30 is 1/2, or that's 50%, or 0.5. So there you go. James surveyed people at school and asked whether they bring their lunch to school or buy their lunch at school more often. The results are shown below. All right, people that bring their lunch, 46 males and 254 females. People that buy their lunch, 176 males, 264 females. Okay, the events male and buys lunch are not independent because. Okay, so just like the previous problems that we've done, the main thing to understand is that if you want to show whether or not two events are independent, you have to do this. Okay, male and buys lunch. So the probability of male given buys lunch. we would check to see if that's equal to the probability of male all by itself. If these are equal, then those two events, male and buys lunch, are independent. If they're not equal, then that means that they are not independent. So it's all about doing those calculations and seeing what we get, and that'll tell us the answer. So let's find the probability of, first let's find the probability of male. Alright, now I think it would be helpful just to go ahead and make a chart. So people that bring their lunch, we have 46 males and 254 females. Alright, people that buy their lunch, we have 176 males and 264 females. Alright, I think the table is very helpful. Now I left these other columns and rows for the totals. So we'll just put the totals here. I'm just going to put T for total and T for total. Alright, total number of males, 222. Total number of females, 518. Now let's find the totals this way. Total number of people who bring their lunch, 300. Total number of people who buy, 440. If you add those up, you get 740. By the way, that'll be the same if you add up the total males and total females. That's also going to make 740 because that's the total number of people, either way you look at it. Anyway, now it'll be easy for us to use our chart to answer this question. So let's start by finding the probability of being male on this chart. Alright, probability is target over total. So we're looking for the number of males divided by the total number of people. Alright, so the number of males is 222 out of a total of 740 people. Okay, I'm just going to put that in my calculator. 222 divided by 740, that is 0.3. Okay, so now we're going to find this other thing. Alright, now we're about to find this. We're still finding the probability of being male on this chart, but given buys lunch. Alright, we're given this. Now, if you're given something, alright, in this case we're given that we're talking about people who buy their lunch, that is the universe. What you're given is the new universe. Whoops, I'm highlighting the wrong thing. So, buys lunch is given, so that means this is what is given. That means the rest of the chart I can black out. Alright, forget about people who bring their lunch. We're given that we're talking about people who buy their lunch. So these totals will now be incorrect. Alright, because these are the totals. Okay, now in this smaller lunch buying universe, again we're looking for males. So again we're going to do target over total here. Alright, so males. There are 176 males in this small universe out of a total of 440 people. Okay, and again I'm just going to put that in my calculator. So 176 divided by 440, that is 0.4. Okay, so these events are not independent because these values are different, and now we know what they are. Okay. Alright, just scanning down to find the one that matches what we found. It looks like it's going to be the last one. Alright, this one right here. All right, they are not independent because the probability of being male given buys lunch is 0.4, and the probability of just being male by itself is 0.3. So it has to be the last one. Bart found 20 quadrilaterals in his classroom. He made a Venn diagram using the properties of quadrilaterals, comparing those with 4 equal side lengths, E for equal, and those with 4 right angles. That's R. Given that a randomly chosen quadrilateral has 4 right angles. Okay, so given 4 right angles. All right, that 4 right angles, that's R. So we are given, we are being given R. All right, that means we're living in an R universe. All right, I'll come back to that. What is the probability that a quadrilateral also has 4 equal side lengths? Okay, so we're being asked to calculate the probability of having 4 equal side lengths, so the probability of E given R. Okay, express your answer in percent form, nearest whole percent. So the key is that what we're given. So we're given R, so that means R is the universe now. If R is the universe, that means everything outside of R no longer exists. So all this out here is gone. All right, R is the universe. That's what given means. All right, now I'm just going to leave E, the letter E, showing just enough to remind you that when we look at universe R, we see these two numbers, 2 and 6. All right, so universe R includes 8 quadrilaterals. But remember that 2 was originally contained in circle E. So this is part of the overlap here. So this number 2, yes, it's in circle R, which means that it has 4 right angles. But it's also in circle E, which means it has 4 equal side lengths. So just remember that 2 does belong in the blue circle as well. So now, given this smaller universe R, what is the probability of E? Well, probability is target over total. So we're looking for the number of E's divided by the total of the universe. So remember this, there's 2 in this universe that were also part of E. So that's target over total in this smaller universe of 8. All right, 2 over 8, that's 1/4. That's 0.25. That's 25%. So that should be the answer. And there you go. All right, which probabilities are correct? Check all that apply. And we're using this Venn diagram here. So let's see, the probability of A given C. Let's calculate that. Well, if we are given C, that means that C is the universe. So what I like to do is, if C is the universe, I sort of black out everything around C to really give you the feel that C is the universe. All right, so I'm going to black out all these other numbers. These are the only numbers that exist now. Alright, so in this smaller C universe, we're supposed to now find the probability of A. Okay, so within this universe, we're looking for target over total, A over total. Well, looking at A up here, you know that the 6 and the 8, these are the A's. So 6 plus 8 is 14. So that's going to be target over total. So it's 14 A's out of a total, okay, of 21. So for the probability of A in this universe is 14 out of 21. That does reduce down to 2/3, so that is true. Okay, so reset. Now, next one, probability of C given B. Well, if we are given B, that means that B is the universe. Alright, so you can forget about these numbers out here. B is the universe. Okay, so we're supposed to calculate the probability of C now in this smaller universe. So, these are the C's within this smaller universe. There's 11 of those. So we're doing target over total, 11 C's out of a total. I'm just going to add all these up. That's 27. So that's 11 out of 27. And yeah, that doesn't reduce. And here this says 8 out of 27. So that's wrong. Okay, now we're supposed to find the probability of A. And we're not given anything. Okay, so the probability of A, target over total, that's the number of A over the total number. Now the number of A turns out to be 31. That's just what you get if you add up these four numbers of A. And the total number turns out to be 59. That's what you would get if in addition to those you added in the rest of the numbers. So that should be the answer. 31 over 59. Alright, that's exactly what we had. So that one is correct. So let's use that same technology to calculate the probability of C. Alright, so this should be the number of C divided by the total number. Alright, the total number is not changing, so that should still be 59. So it's just a matter of what's the total number of C, which is, that's 10, that's 11, so that's 21. So 21 out of 59. Okay, and that is not what they have, so that's wrong. Now, the probability of B given A. Given A, that means A is the universe. Gotta love it. Alright, let me just clean this up a little bit. So if A is the universe, that means everything else goes away. A is the universe, so forget about all these other numbers. Okay, so now in this smaller universe, we're supposed to now calculate the probability of B. Okay, so the probability of B, target over total, so that should be the number of B divided by the total number. Now, this number of B, though, will not include anything that's outside of this universe. So, how many B's are there in universe A? Well, these are the B's, because you can tell from the orange circle here that's inside of universe A. Alright, so putting those together, we're looking at 13. So that's the number of B's. Now the total number is if you add all 4 of these up. So that's 31. So 13 out of 31. Oh, but they have 27, so that's wrong. So I think it's only these first two, well, not the first two, but it's only these two that I have checked that are correct. And there you go. The cable company is analyzing data from 2 satellite television providers to determine whether their users spending more time watching live television or shows that have been recorded. Satellite company X, 89 live, 430 recorded. Satellite Y, 65 live, 94 recorded. I am going to go ahead and make a chart out of this. Alright, so these are the 4 numbers that are just given to us straight out. And I'm just going to fill in the totals now. Alright, so here it is with the totals filled in. Now, to the nearest whole percent, what is the probability that a randomly selected customer from satellite company Y watches recorded shows more often than live television? Well, they're telling us right away that we're talking about satellite company Y. So these are the only numbers that we need to worry about. So we really could just forget about the rest of this information. All right, a selected customer from satellite company Y. So we're given Y, so that's the universe that we need to focus on. Now, what were they asking us again? What's the probability that someone in this smaller universe watches recorded shows? All right, so we're looking for the probability of recorded out of this smaller, considering that we already know we're talking about satellite Y. So target over total people. The target is the recorded people, so that's 94 out of a total of 159. Okay, I'm just going to check, see if this, wait, they want a percent, so I'm just going to put this in my calculator. Well, you know what, I'll show you this time. Alright, 94 divided by 159. Okay, that's this, so 59%. Nearest whole percent. Alright, let's see if that was the answer. And there you go. Well, consider a single spin of the spinner. Which events are mutually exclusive? Check all that apply. So things that are mutually exclusive are things that can't happen at the same time. Alright, we're looking for things that can't both be true. You can't flip a coin and have it be heads and tails at the same time. Heads and tails are mutually exclusive. Okay, so landing on a shaded portion and landing on an even number. Well, there's one that's shaded and even. They're both happening at the same time, so that is not mutually exclusive. So that one's okay. Landing on a shaded portion and landing on a number greater than 3. Alright, there we go again. We're on a shaded portion and a number greater than 3. So, both things happening together, not mutually exclusive. So that's not the answer. Okay, or an answer. Landing on a shaded portion and landing on 3. Well, there is only one number 3 and it's not shaded. So you're either going to land on a shaded or you're going to land on 3. Both of those things cannot happen at the same time. So that is a pair of mutually exclusive events. Now, landing on an unshaded portion and landing on an odd number. Okay, well, here's an unshaded portion, and it's also an odd number. So those two things are happening at once, so they are not mutually exclusive. Okay, let me just clean that up. Last one. Landing on an unshaded portion and landing on a number less than 2. Okay, so these are the unshaded portions. Are either of these less than 2? No. 2 is not less than itself, so neither of these are less than 2. So there's no way for you to be unshaded and less than 2 at the same time. So these two events are mutually exclusive. And there you go. Pedro has determined that the probability his shot will score in a lacrosse game is 30%, 0.30. What is the probability that he will score on 2 consecutive shots? Well, these are completely independent events. Him scoring on one shot will not affect his score on another shot. So the probability of 2 events happening that are completely independent is just the product of those 2 events. So it should just be, well, I went to erase it, but it's already gone. It should just be 0.30 times 0.30. All right, that should be the probability of both things happening together, or like in a row. All right, so that's 0.09. So it should be the first one. Cha-ching. And there you go. A spinner is divided into 8 equal-sized sections, numbered 1 to 8. What is true about spinning the spinner one time? Check all that apply. Well, here's a rough sketch in case we need it. So S equals brat. This S is the sample space, which means just a list of the possible outcomes. And yeah, we have 1 through 8. So, and here we have 1 through 8. So that's true. If A is a subset of S, then A could be 1, 2, and 3. Well, yes. 1, 2, and 3 is a subset of S. Okay, if A is a subset of S, A could be 7, 8, and 9. Nope. 9 is not part of S. So you can't have a subset that has an extra number in it that's not in the original set. If a subset of A represents, not a subset of A, if subset A represents spinning a number less than 4, then the sample space for A is 1, 2, 3, 4. No, because 4 is not less than 4. It's equal to 4. So that's a no. If a subset A represents the complement, all right, as soon as I see the word complement, I always think the word not really big. The complement of spinning an odd number, okay, that would mean not spinning an odd number. In other words, that would mean spinning an even number. So that would be 2, 4, 6, and 8, which is what they had, so that's true. So these are the 3 true statements. And there you go. Christina is randomly choosing 3 movies to take on vacation from the 9 action movies, 7 science fiction movies, and 4 comedies. Which statement is true? She's choosing 3 movies. Okay, let's talk about the total. Alright, 9 plus 7, that's 16 so far. And then 4 more, so that's 20. So we're talking about 20 total. So, before I even see what these different possibilities are, I know that the total number of ways, like combinations of 3 movies that she could pick, is 20 choose 3. Alright, I'm talking about combinations because the order doesn't matter. We're just doing groups of 3. Alright, it would be the same movies no matter what order you mention them. Alright, so this is the total number of ways she can pick 3 movies out of what she has. Okay, let's break down the individual ones. Which statement is true? So it sounds like only one of these is going to be true. The probability that Christina will choose 3 comedies can be expressed as 1 over this number. Well, that's not going to be it. See, this is the total, which is what we just discussed. So we're always going to be doing target over total. So if the target is, what we say, comedies, then target over total, well, there are 3 comedies, which is 4 comedies. So that would be 4 over this number. And that's it. So that would be that probability of that one. So that one's not it. Now the probability that Christina will choose 3 action movies. Okay, 3 action movies. Alright, so there are 9 action movies. So that means we're picking 3 action movies out of 9. So that's 9 choose 3. So we're doing target over total. So the target is how many ways we could pick 3 of the 9 action movies. That's 9 choose 3 out of a total of 20 choose 3 that we spoke of right from the beginning. So let's see, is that what they have? Nope, they have 20 choose 3. This is upside down. It's target over total, and this will always be the total. Alright, how about the third one? Let's have a quick little side lesson. If I said I wanted to talk to you about the probability that it's going to rain. Alright, now what if I told you that there is an 80% chance of rain? That means the probability of raining is 0.8. What would be the probability of not raining? Let's see. Alright, it's 80%. Why does my decimal keep going away? Alright, if the probability of raining is 80%, can you guess what the probability of not raining is? Alright, the probability of not raining should be 20%. Alright, because those are the only 2 options. Either it's going to rain or it's going to not rain. Alright, so in other words, I did 100 minus 80, and that gave me the 20%. But if I want to deal in decimal form, if the probability of raining is 0.8, the probability of not raining is 0.2. Now, here's the key part of this lesson, all right, because obviously that's the 20%. But just like when I'm dealing with percents, I did 100% minus 80. In decimal form, if I want to find the probability of something not happening, what I'm doing is I'm subtracting from 1. If I do 1 minus the 0.8, that gives me the 0.2. Okay, just like 100% minus 80% becomes 1 minus 0.8, and that gives me 0.2. Okay, so that's important. So just remember the probability, see if the probability of A is whatever it is, the probability of not A is going to be 1 minus the probability of A. Alright, so what does that have to do with this up here? Alright, so here they're saying the probability that Christina will not choose all comedies. Alright, so if the probability that Christina will choose all comedies alright, whatever that is, then the probability that Christina will not choose all comedies is going to be 1 minus this. All right, it's going to be 1 minus the probability of all comedies. Okay, that's how you get the not. Probability of something not happening is 1 minus the probability of the original thing. All right, it's just like I was saying before down here with the rain. So we need to figure out what the probability of all comedies is, and then whatever that is, the probability that she does not do that will be 1 minus that. Okay, so probability of all comedies. So all comedies, how many comedies are there? There are 4 comedies, but we're only picking 3. So target over total. So the number of ways that you could have all comedies is 4 choose 3. Okay, because we're choosing 3 out of a total of 4 comedies. So 4 choose 3 out of the total number of ways that we could choose 3 movies. So target over total. So this represents the probability of all comedies. So if we want to do not all comedies, we need to do 1 minus this. So 1 minus 4 choose 3 over 20 choose 3. Is that what they have? Oh, so close. But it was it's 20 choose 3, not 20 choose 4. So it must be the last one. Okay, if I want to talk about the probability that Christina will not choose all action movies, first of all, I need to talk about the probability that Christina will choose all action. Alright, I need to figure out what that is, because the probability of not choosing all action should be 1 minus the probability of all action. Alright, so let's start by finding the probability of all action, choosing all action movies. And so that'll be target over total. And as we've been doing for all of these questions, the total is 20 choose 3. Okay, because we have a total of 20 movies and we're choosing 3. But if we're going to pick all action movies, That's our target, is all action. So let's think about how many ways you could choose all action movies. Well, there are 9 action movies, but we're only picking 3. So the total number of ways to pick all action movies are 9, choose 3. Okay, so this is the probability of all action movies, target over total. The number of ways you can go action divided by the total number of ways you can pick your 3 CDs. Now, the probability of not all action is going to be 1 minus this. So it should be 1 minus 9 choose 3 over 20 choose 3. And finally, that is what they have. So last but not least, the last one is the right one. All right, I know that was kind of complicated. I hope that helped. Jillian has 3 different bracelets, X, Y, and Z, to give to her friends as gifts in any order she prefers. If bracelet Y is chosen first, in how many ways can Jillian give out the bracelets? Okay, this is pretty simple, I think. They're saying if bracelet Y is chosen first, so let's say if Amy chooses bracelet Y. Okay, so that's done. So then, given that, in how many ways can Jillian give out the bracelets? Well, because we know that Y is chosen first, so after that, Beth could get bracelet X, and Carla could get bracelet Z, or Beth can get bracelet Z, and Carla can get bracelet X. If we're given that Y is already spoken for, there are only 2 possible ways to give out the bracelets. So 2. By the way, I just made up Amy, Beth, and Carla as examples. You won't find those mentioned anywhere in the problem. All right, U basically stands for universe. So consider U, the universe here, is a set of all x such that x is a positive integer greater than 1. Now, integers are numbers that are not decimals or fractions. So integers include numbers like -4, -3, -2, -1, 0, 1, 2, 3, 4, etc. But they're saying positive integers greater than 1. So we can forget about all of these integers and even this one. All right, it says greater than 1, not equal to 1. So we're talking about the set of numbers 2, 3, 4, and so on like that. So that's what set U really is. Now, which is an empty set? All right, empty set means there should be no number that satisfies both things. So x is an element of U, and half of x is prime. If it's going to be empty set, then there should be no numbers in both sets. So just as one example, 6 is an element of U, and half of 6 is 3, and 3 is prime. So yeah, that satisfies both. X is 6 satisfies both situations, so that's not the empty set. Okay, alright, how about the next one? X is an element of U, and double X is prime. Well, that's automatically the empty set. Alright, I should have mentioned this when I said, oh, 3 is prime. Maybe you don't know what prime is. Prime numbers are numbers like 2, 3, 5, 7, 11, 13, 17, okay, 19. Alright, what all of these numbers have in common is that the only way to write them as a product is using the number 1. Alright, 2 can only be written as 1 times 2. There's no other way to do it. 3 can only be 1 times 3. 5 can only be 1 times 5. So for example, the number 9 is not prime because I could write the number 9 as 3 times 3 and, whoops, I wrote 1 times 3. 9 can be written as 3 times 3 and 1 times 9. But for prime numbers, it's only the 1 times itself. Okay, but if you take any number and you multiply it by 2, there's no way it's going to be prime. Okay, so if I take these numbers and I double them, alright, then I'm going to get 4, 6, 8, 10, etc. These are all even numbers. They can all be written as 2 times something. So they will not be prime. Alright, so therefore since there's no way to take an element of U, 2, 3, 4, and double it and then have it be prime, there's no way for both of those things to be true. Then that means we're looking at the empty set. Boom. Alright, this diagram shows the number of children who have ever used motorized scooters, manual scooters, and or bicycles. Okay, what about it? Which combination represents the empty set? Remember, the empty set, that means there should be nothing included in that set. So if we're going to talk about the union of two things, which is what this symbol means, or the intersection, alright, so this means union, and this means intersection. If it's going to be the empty set, then we're looking for there to be no overlap. So really, as soon as I see them, we're shooting for the empty set, I'm thinking intersection. Okay? I'm thinking, alright, if you have two sets that don't touch, then like say if this is set A and this is set B, if there's no overlap, then if I say, okay, what's the intersection of A and B, then that's the empty set. Alright, because there is no intersection. If I took the same picture and I said A or B, well, it doesn't matter that they don't overlap, because this symbol means just take everything in both. So if there were 10 people in group A and 5 people in group B, then A union B, we'd be looking at 15 people. Alright, so if we're shooting for the empty set, you pretty much have to be talking about intersection. Alright, the only way you're going to have a union and have that be the empty set is if both sets were empty in the first place, which would be silly. So let's think intersection. Alright, since we already know that none of these sets are empty, so union is not going to get it for us. So it's not going to be this, it's not going to be this. It's going to be one of these. So let's look for the one where the two sets are not touching. Motor and manual. Well, those are overlapping. Okay, so the intersection would be 24. It would not be the empty set. So it better be this one, motor and bicycle. Yeah, you see motor and bicycle, there is no overlap between these two. So the intersection would be the empty set. They have nothing in common. So it's going to be this one. This Venn diagram shows the number of patients seen at a pediatrician's office in 1 week for colds, ear infections, and allergies. Colds, ear infections, and allergies. Okay, so that means there were 5 children that came in for something different other than colds, ear infections, and allergies. All right, how many patients had allergies or ear infections but not both? Okay, so let's talk about that. Allergies or ear infections. Okay, so here's allergies. And here's ear infections. Alright, so allergies or ear infections would include everything inside of these circles. But then it says, but not both. And here in the overlapping part, these are the kids who had both ear infections and allergies. Alright, so it says, but not both, so we want to go ahead and throw those out. Alright, so these remaining ones, okay, I thought that was going to be yellow. These remaining ones are the kids that have had allergies or ear infections, but not both. So I'm just going to add all these up. So let's see, 10 and 15, that's 25. Plus 9 would be 34, and then 2 more would be 36. So let's go with 36. And there you go. Look guys, that's going to do it for this video, longest video ever. And hopefully this will help you do well on your test. Good luck.